Hello students, I am Joanna, your virtual tutor for the day. It has been brought to my notice that most of you are struggling to understand different processes of thermodynamics. So, here I am, all set to explain to you the different cycles and flow processes of this system. Let's get started. What is a thermodynamic process? The passage of a thermodynamic system from the initial to the final stage of a thermodynamic equilibrium is defined as the thermodynamic process. The system consists of certain properties like volume, pressure and temperature. The process undergoes a change from one thermodynamic state to the final state due to changes in properties like volume, pressure and temperature. The thermodynamic system includes isothermal process, adiabatic process, ISOCHORIC process, ISOBARIC process and reversible process. Today, I will be explaining each of these processes. Types of thermodynamic processes. Isothermal process. The temperature remains constant despite the system undergoing a change from one state to another. The thermal equilibrium in an isothermal process stays the same. Now ask me why? It's because the process of heat transfer into or out of the system takes place very slowly. The term iso means equal. So, the term isothermal stands for equal heat. It defines the entire functionality of thermal equilibrium. Here's an example of the isothermal process to help you understand. Let's assume that a beaker is placed in a tub full of water. Let the beaker contain the base. Now, slowly add the acid to the heat. The acid and base will react with each other to form salt. You will gradually observe heat generating from the process. Since the acid is added slowly, it gives the time to transfer the heat from the beaker to the tub. So, what can we derive from the example? The heat of the beaker remains constant. This is how an isothermal process in thermodynamics works. Adiabatic process. It refers to the process where the heat content of the system remains constant. The transfer of heat between the system and its surroundings does not take place in this process. Take a close look here. The diagram represents the pressure versus volume graph of an adiabatic process. The area under the curve represents the work done during the process along with the curves we can see between the starting and ending volumes. The term adiabatic efficiency is applicable for devices such as nozzles, turbines and compressors. That brings us to the next question: how do we find out the adiabatic efficiency of a steam turbine? You need to calculate the ratio of the work done per unit mass of steam and the heat energy released. Pay your attention here. The ratio should be calculated in a way that it is theoretically capable of transforming into mechanical work during the adiabatic expression of a particular unit weight of a system. Isochoric process. The volume of the system remains constant during this process. You must have heard of heating of gas inside a cylinder? That is an example of the isochoric process. Here's the crack. The processes 2 to 3 and 4 to 1 are isochoric processes. Although no work is done on the systems, the heat gets transferred from the system 2 to 3 to the system 4 to 1. Take note that the isochoric processes 2 to 3 is supposed to represent the ignition of the fuel-air mixture and the subsequent process of rapid burning. Isobaric process. The pressure of the system remains constant during the process. Suppose there is fuel in the piston and cylinder arrangement. When the fuel is burned, the pressure of the gases is generated inside the engine. As more fuel burns, more pressure is created. Let us assume there is an isobaric heat addition in an ideal gas. The molecules do not interact. Also, they do not have volumes. The pressure varies with the temperature and quantity linearly and inversely with the volume according to the ideal gas law. We can derive PV is equal to nRT. You must take note that P is the absolute pressure of the gas. N is the amount of substance. T is the absolute temperature. V is the volume. R is the ideal or universal gas content that is equal to the product of Avogadro constant and Boltzmann constant. The isobaric process and the ideal gas law can be represented as V by T is equal to constant, or V1 by T1 is equal to V2 by T2. Reversible process. In this process, the final properties of the system can be reverted to its original property. The process can be perfectly reversible only if the changes are small. Example: a change in the internal energy characterizing any particular process can be distributed in numerous ways between the work done on, or by the system and heat flow, across the boundaries of the system. We can explain this phenomenon with the help of the first law of thermodynamics. Delta U is equal to Q plus W. Each combination of Q and W represents different dimensions between the initial and the final states. The internal energy U of a system is the sum of the kinetic and potential energies of its molecules and atoms. Microscopically, we can define the change in internal energy delta U to be the one that is stated by the first law of thermodynamics. Now that you have an understanding of the thermodynamic processes, try implementing the concepts to solve the equations. Do not forget to share your feedback in the comments section below. In case you have queries, do not hesitate to contact me at MyAssignmentHelp.com.